Welcome to Linear Equations. It sounds innocuous enough. How hard can a linear equation be? And the answer is basically impossible. So, with that out of the way, we're going to introduce what linear equations are in this video. We'll have some definitions. We'll kind of give an overview about where we're at in this chapter. We're getting close to finishing it. And I promise that unlike the last section, I will not lie to you, and I will actually answer the question I'm posing to you in this first video. So to start off, we're going to be doing analytic stuff again. We had a fair amount of time in qualitative analysis land. Remember, the three things that we're always doing to look at differential equations are analytic methods, solving them by hand, qualitative analysis, which is like slope fields and analyzing the equations and the functions and linearization and bifurcations, lots of things that we can do qualitatively to analyze something, and also numerical solutions, which we've only found with Euler's method so far. All right, so we're going to end chapter 1 with two sections on analytic methods, specifically for linear equations. So without further ado, let us jump right into it. Good news and bad news. The good news is that this section is pretty manageable. The bad news is that most ODEs, even nice ODEs, even linear ODEs, don't necessarily have solutions, or certainly not solutions that we can write in terms of elementary functions like sines and cosines and exponentials and stuff like that, unfortunately. So that's kind of the bad news. And then even a lot of these techniques that we do by hand, like separable differential equations and method of undetermined coefficients, which we'll talk about in this section, and then integrating factors, which we talk about in the next section. Most of those are just usually done by computers anyway. So like something like Maple or Mathematica, but I'm really kind of talking a lot. Let's get into some definitions. That's what everyone loves, right? So before I answer this question, and we're right about to answer the question, well, what's a linear function, right? You know what a linear function is. Y is equal to mx plus b. A linear ordinary differential equation is going to be basically a linear function, just a little different, right? This will become a derivative, and this is going to depend on time. So what we're going to get is a first order linear ordinary differential equation is of this following form: dy dt equals some function of t, and it really can be anything, times y plus another function of t. And we'll be writing it this way for now. In the next section and kind of moving onward, we'll be writing this in a different form. So far, we've always just been writing the left-hand side as the derivative, because that lets us call this some function of t and y, which lets us do really powerful things with slope fields and other qualitative analysis. But later on, we'll be shifting things around a little bit. There'll be a new general form, essentially, a new standard form, if you will. All right, when your cat climbs on board games, sometimes they fall. She's like playing Jenga over there in my closet. Okay, so this is what we have. And again, I should really point out, right, these two functions don't have to be linear. So A and B can be as messy as you want, but they do have to only depend on time. So let's look at some examples of linear ordinary differential equations, and we'll just worry about first order for now. So we could have dy dt equals t squared y plus cosine of t. Again, cosine and t squared are not linear functions, but it matches the form: a function of t times y plus a function of t. Right, here is our a of t, and here is our b of t. We could look at a different differential equation, y dot. Again, remember, y dot means the derivative of y with respect to time. It's not prime. Prime is any derivative. The dot specifically denotes with respect to time. That could be e to the 4 sine of t, all divided by t cubed plus 7t times y, plus the sine of t minus e to the t squared, right? It can really look much worse than what we had. But again, this is just some function of t. And this is just some other function of t. So it's still a times y plus b is equal to the derivative. And I can go on, right? We can use other variables. It could be dp dx minus 3p is equal to x times p plus 2, right? It doesn't have to be in standard form, right? We can add the p over to both sides, right? If you add the p over to both sides, what do you get? You get 3p plus xp. That's 3 plus x of those p's plus 2, and it's still some function. Again, it doesn't have to be time. A lot of times our independent variable is time, right? But it's still some function of our independent variable times p, our dependent variable, plus some other function of our independent variable. And the second one is a constant coefficient, or a constant function. Now my cat's sitting on my notes. Don't worry. The animals really in this house are really trying to get in the way of your learning. But yeah, those are some first order linear differential equations. We could also give you some other examples, right? dp dt equals y squared. Now this is not linear. These are all linear. This is not a linear differential equation. It's a very nice differential equation. It's a separable differential equation. It's an autonomous differential equation, but it is not linear. Autonomous and separable differential equations are very nice in a lot of ways. And again, there's really a lot of definitions in this class. Linear differential equations are also nice in a lot of ways, but this is not linear. Okay, so we'll use a different color. These are not linear. Another example of something that's not linear is dz dt equals t times sine of z. Again, this is not a bad differential equation. And it's also a separable differential equation. We can also solve it. But it is not a linear differential equation. Linear means function of t times y plus another function of t. So those are linear and nonlinear differential equations. We're going to end this video with 3 more definitions, or 6 or 2. It depends on how you count. We got a couple more definitions. So here's a couple definitions for you. If we have a linear differential equation with b of t equals uniformly 0, and you did see that right, I wrote an equal sign with 3 horizontal bars. And what that means is it doesn't just mean it equals 0 sometimes. That means it equals 0 always. So a little notation, right? That means 0 always. Okay? Or it could be uniformly equal to 1, but usually we call it uniformly equal. At least in my experience in grad school. The book doesn't use this, but it's a nice notation. And it is pretty standard. Okay, so what happens if that's the case? Essentially, what happens if there's no y-intercept for linear equations? Of course, it's not a y-intercept for the differential equation, but what happens if that's 0? Well, if that's 0, we call it non-homogeneous. Sorry, we call it homogeneous. Which I always thought was homogeneous. But no, homogeneous is like saying something about milk or something. Homogeneous is something else, all right? It is also called unforced, which is honestly a term I had not heard before. But we'll be talking more about that term with some applications, physics applications, later on in this class. And what happens if b of t is not equal to 0, October? Well, if b of t is not equal to 0, well, the cat that's not on the notes would tell you that it's probably non-homogeneous. And that is indeed true. All right. Not surprisingly, if it's anything other than 0, it's not homogeneous. What do you think it's going to be called as the second thing? Yeah, you got it. It'll be called forced. And we have one more definition. And specifically, this last definition is if a of t is uniformly equal to a lambda, then we call it a constant coefficient differential equation. All right, and there will be many nice things that we can do with constant coefficient equations. And again, b doesn't have to be constant. It's specifically if this part is constant, if everything attached to y's is constant, then we're good to go. And that's kind of one of the ways of remembering these definitions. Most of these definitions have to do with the dependent variable. Linear makes no claims about b and a. Linear just means the derivative and the y part is linear. Like it's not y squared, it's not the derivative squared. When we talk about second order linear, there will be a second derivative, but that also has to be linear, right? We can't have sine of y prime or something like that. Linear just means, we're mostly just talking about the dependent variable with these definitions. Constant coefficient just talks about the coefficient of the dependent variable, all right? So something can be constant coefficient, even if this guy over here is not constant. Okay. So we got some definitions, we got that out of the way. We talked roughly about what linear differential equations are. We introduced this section, and in the next video, we'll talk about linearity principles. Until next time.